Is it okay now?
Yes, sir. It's visible in the Teams.
It is okay, na? Okay.
Sir, please wait 1 2 minutes so that people can join.
Okay.
Like the
I am waiting. So as you told, maybe this is actually a third year course, third year, not second year. Okay. So if you want to move early, maybe 10 minutes early, you can tell me. I will leave you before, so that you can comfortably go. Okay. Because this is first hour, no problem. Okay. So I'm again explaining. So generally, the transportation problem, so is presented either in the equation form or in the matrix form. Generally it is in matrix form, not in equation form. So here you see in this problem, the variables are missing. So in every cell there is a variable. With respect to first cell, the variable is x11, second cell row wise I'm talking x12, and the first row, that is with respect to C1n, the variable is x1n. And second row, similarly, variables are x21, x22, x2n. And the last row, mth row, the variables are so xm1, xm2, xmn. These are the variables. There are how many variables altogether? M into n number of variables. There are m into m number of cells. So these variables are unknown. We have to find in this problem, we have to find these variables. So if you see this problem, if you see here, this is the problem. So it is a very complicated problem. Means generally, if you are solving using the simplex method, so you have to spend a lot of times. So you need not solve it by simplex method. We have to solve it by some special algorithm called transportation algorithm. So how many variables are there? M into n number of variables. How many constants? M plus n number of constants. All are equally type constants, and the problem is minimization type. In case the problem is given maximization type, change into minimization type and solve it. Okay, this. So this example, this particular example, what is given here, the numerical example. So it is a unbalanced transportation problem. So due to the unbalanced transportation problem, one dummy sources has been included so that the problem is balanced. Once it is balanced, the problem has to be solved. For the dummy sources, the cost coefficient is 0, 0. There are a row, only 2 elements are there. So how many rows are there? Row 1, row 2, row 3, row 4. 4 rows. And how many columns? There are 2 columns. So this 4 rows stands for 4 different sources, and 2 columns stands for 2 different destinations. Sum of destination you can see 3700, and some of the row elements 1000, 1300, 1200, and 200. That is it. Okay, that is also 13700. So the problem is a balanced transportation problem. Okay, so here see another problem. So another transportation problem where transportation the from sources, that is from the refinery, and the destination, the distribution area. How many sources? The sources 1, 2, 3 sources are there, and how many destinations? There are 3 destinations. So D1, D2, D3, and if you count here, and what are the availability? 6, 5, 8, 6, 5, 11 plus 8, 19, and demand 4 plus 8, 12, 12 plus 7, that is 19. So this is a balanced transportation problem. So here I like to mention here, say we are transporting the products from source to destination. From first source to first destination, the transportation cost per unit transportation cost is 12 unit. Then for the second one it's 18, and there is in the third cell there is M. This M stands for is a big number. The transportation cost is huge. So When there is, you see, we are looking for minimum transportation cost, minimized transportation cost. When M is large, so we have to avoid this cell. And similarly, second row, the transportation cost per unit transportation cost 30, 10, 8, and third row transportation cost 20, 25, and 12. Okay, this. So this problem is balanced one, but what M stands for? M indicates a very big positive number, means, so if you consider this AM, so we have to pay more transportation cost, so we are avoiding. Okay, so wherever there is a M, so M is large, so we have to avoid this. Okay. Now you can see in this problem, as I've already mentioned, so how many sources? There are 3 sources, source 1, source 2, source 3. And what are the availability? 6, 5, 8, 11 plus 8, that is 19 units. And the demand, actually, if you forget about the dummy, so you have here 4, 8, 4, that is 12 plus 4, that is 12 plus 4, 16. So if you leave the dummy, so only 16, but it is 19. So one dummy demand point is included. Dummy demand point is included. You can see here. So what are the demand there? That is 3 units. So if you include this, then we have here 6, 5, 8, that is 19, and 4, 8, 4, 12 plus 3, that is the 16 plus 3, that is also 19. So this is becoming a balanced transportation problem. These are the example, but we have to solve such problem. Okay. So this examples is no way we are bothering. We are bothering some problem, say whether it is a balanced transportation problem or not. If it is balanced, then we solve it. If it is unbalanced, we have to make it balanced and solve. Balanced, directly will solve. If it is unbalanced, we'll make it balanced and solve. So if it is unbalanced, either you add a fictitious source or a fictitious demand, depends on the need, then we solve. Okay. Now this next section say determination of starting basic feasible solution. When you formulate the simplex table, from the initial simplex table, we find the trial solution or the basic feasible solution. So here that is not the case. It is a different one. Say how to fulfill, how to satisfy the source and demand. So how to start a basic feasible solution. So that is our main aim, and that is called phase 1 solution. And we solve the problem, transportation problem, in 2 different phases. Phase 1, in phase 1, we'll find a solution. And what should do? If you find a solution, the solution may be optimal, may not be optimal. Then in phase 2, we'll check whether the given solution is optimal or not. If it is optimal, we stop. If it is not optimal, we try to improve the solution. So using the phase 2 rule, but we'll discuss how to improve, how to find the phase 1 solution, and how to find the phase 2 solution, and how to improve. Okay. Now next part is determination of starting solution or the phase 1 solution. In any transportation model, generally we are talking about the balanced transportation model, we determine a starting basic feasible solution, and then iteratively we move toward the optimal solution, which is the least shipping cost. Our main purpose, we minimize the transportation cost or we minimize the shipping cost. So first we'll find the phase 1 solution, and this phase 1 solution we'll try to improve. So if it is minimum, we'll stop, otherwise using the phase 2 solution we'll minimize. There are few methods. There are 3 methods. So generally we talk about the 2 methods. There are 3 different methods. There are 3 methods to determine the starting basic feasible solution. Okay, any basic feasible solution, if you are considering a basic feasible solution, it has m plus n minus 1 basic variables. M plus n minus 1 basic variable, which may assume non-zero or we say it is positive. These many basic variables. No basic variable is negative. So basic variables has to be positive. Sometimes also you can say 0, but 0 we avoid. So, and we mention here, we have m plus n minus 1 number of basic variable. M plus n minus 1 number of basic variable, because there are m plus n number of equally type constants. And since the problem is a balanced one, due to the rim condition, only m plus n minus 1 number of equations are linearly independent. Due to that, we have only m plus n minus 1 number of basic variables. One you can leave, one constant you can leave. Okay. So the remaining, these many variables are generally positive, we say non-zero, and remaining variables will be non-basic variables. They are all 0. In any transportation table, we only indicate the basic variables. Basic variables, those are non-zero we indicate. Others are by default they are 0. The cell corresponding to non-basic variables will be blank. So basic variable, non-basic variables, if it is positive we indicate, if it is nothing there we don't indicate anything. Okay. There is one more point. Degenerate basic feasible solution. Degenerate. If in a cell we find a 0 mentioned, so it means that that cell corresponding to a basic variable which assume a 0 value. So as I already mentioned, there has to be m plus n minus 1 number of basic variables. In m plus m minus 1 number of basic variables, if you find there is a further 0, if anyone are 0, any variable is 0, then the solution is known as degenerate basic feasible solution. Okay, so if you set it 0, there is problem. We have to, instead of 0, maybe we say it is, say epsilon, and the small positive number, then we proceed. Okay, in simplest language, we say that the solution is degenerate. Okay, if you find one of the basic variable, at least one of the basic variables are 0. Okay. Now, few methods I mentioned. There are 3 methods. One is called northwest corner rule method. Northwest corner rule method. Another is least cost method. Another is Vogel's approximation method. Okay, Vogel's. But these two are enough. These two are enough. We will only consider northwest corner rule or least cost method. Okay, so before stating this method, I like to mention, you see this problem. So this problem, so already there are some marks are there. You forget about the marks. So I want to explain. So how many sources are there? There are 3 sources, S1, S2, S3. Then how many destinations? Destinations are 4 destinations, D1, D2, D3, D4. And what are the availability? Some marks you can see here. You forget about that. So initially it is 5, 2, 3. 5, 2, 3. So in first source, 5 units of a product available. In second source, 3 units, and third source, second source 2 units, and third source 3 units. 5, 2, 3, altogether 10. And what are the demand? There are 4 demand points. As first demand 3 units, and second demand 3 units, third demand 2 units, and this is also 2 units. 3, 3, 2, 2, that is also 10. So it is a balanced transportation problem. Okay, this problem we are going to discuss. These problems we are going to discuss. You can see here. So northwest corner rule, the method called northwest corner. In the transportation problem, the top one is north, top one is north, and then bottom one is south, and the right one is east, the left one is west. Northwest. Northwest corner, that is the northwest corner means that is the first cell. Cell number C, that is cell 11. Cell 11 represent the northwest corner. Okay. Now, what is the discussion here? The method start at northwest corner cell, that is cell 11. The method start at the northwest corner cell, that is cell 11. Step 1. We allocate as much as possible to the selected cell and adjust the associated amount of supply and demand by subtracting the allocated amount. So how much you can allocate? You can see here. Let us go to this numerical example. See, so in this cell 11, with respect to first source, how much available? That is 5 units available. So in the cell 11, with respect to demand 1, say what is the demand here? This is 3 units. What is the available? 5 units. 3 units available, 5 units available, 3 unit demand. So how much you can allocate to this cell? We can allocate maximum among 5 and 3, maximum value of 5. So the minimum value of 5 and 3, that is 3 unit you can allocate. 3 units you can allocate to cell 11. If you allocate 3 units, what is left out? Out of 5, you subtract 3, so only 2 units available. And so these 3 units already as demand we have allocated. So this 3 minus 3, it is nothing, is there is no demand. Okay, this. So we have allocated 3. So after this allocation, we see further what is happening. Say what is, say this particular column is fulfilled. Once the particular column is fulfilled, we remove the first column. So if you remove the first column, so how to remove? Just to put a line. So we remove in the sense, so first demand is fulfilled. Since first demand is fulfilled, so 3 units gone. Say further we see that the problem is balanced. How it is balanced? Now how much left out? That is 2. In second source it is 2, 4. In third source, it is 3. 2 plus 2 plus 3 is 7. Now demand you can see 3 plus 2 plus 2, that is 7. So still the problem is balanced. So once it is gone, this first column is gone. Say assuming the remaining problem is a transportation problem, is a balanced transportation problem, we like to find out the northwest corner. The northwest corner is nothing but the cell number C12, because the first column is not there. So if you analyze, there are how many? There are 3 sources and 3 destinations. 1 is left already. So C12 is the northwest corner. Now what is happening? Say we like to allocate how much available? Out of 5 already have taken 3. Now only 2 units available with respect to C12. So 2 units available, and in the demand, what is the demand here? Demand is 3 units. So we cannot fulfill everything. So only 1 unit left out. So we have to allocate. So 2 units to C12. 2 units to C12. So these 2 units we can allocate. Okay. So and once you are allocating, what is happening to this? So first we have allocated 3, then 2, nothing is there. But here out of 3 we have allocated 2. So there is a demand of 1 unit. So what is happening? We can remove the first row now because it is fulfilled. First row is dropped. So now what is happening again? So initially first column, then first row. So we observe the remaining problem again a balanced transportation problem. How balanced transportation problem? You can see here 2 plus 3 5 and here 2 plus 2 plus 1 it is 5. So it is a balanced transportation problem. In the same manner we proceed. You can see here. Step 1, we allocate as much as possible to the selected cell and adjust the associated amount of supply and demand by subtracting the allocated amount. Step 2, cross out the row or column with zero supply and zero demand. If you find that is zero supply or zero demand, so cross out the particular row or a particular column to indicate that no further assignment can be made in that row or column. Step 2. So if a row and a column are simultaneously satisfied, then if exactly one row or one column is left uncrossed, make the obvious allocation and stop. See, in the last attempt, you can see here, if both a row and both a column are simultaneously satisfied, let us say it is 2, 2, you are allocating 2, so both are fulfilled. So if both a row and a columns are simultaneously satisfied, then if exactly one row or one column left uncrossed, make the obvious allocation and stop. Else, cross out only either a row or a column. Okay, and leave a zero supply in the uncrossed row or column. See, we have to remove at a times a row and a column. Only at the final stage we can fulfill that. So that we are discussing. Step 3, if no further allocation is possible, is to be made, stop. Else move to the cell to the right if a column has been crossed out, or to the cell below if a row has been crossed out, go to step 1. See what exactly we are doing. See, we are allocating to the northwest corner cell. After allocating, we are reducing that amount in the supply and demand. At a times, we can fulfill either a row or a column. If both are fulfilled, only one of them you can remove, both you cannot remove for technical problem. So here you can see first time we are allocating 3, second time we are allocating 2, then third time we are allocating 1, then fourth time we are allocating 1, then fifth time we are allocating 1, and sixth time we are allocating 2. Now altogether how much you can allocate here? You can see the row wise 2 plus 2 is 5, 1 plus 1 2, 1 plus 2 3, and column wise that is 3, 2 plus 1 3, and 3 plus 1 is 1 plus 1 is 2, then it is 2. So altogether how many cells are there? How many cells are there? 3 into 4, there are 12 cells. So, and 3 sources, 4 destination. Altogether, there are 7 constraints. How many non-zero value we have got? Say 1, 2, 3, 4, 5, 6. 1, 2, that is, see what I'm mentioning here, x11 equal to 3, x12 equal to 2, x22 equal to 1, x23 equal to 1, x33 equal to 1, x32 equal to 2. Okay, these many variables are non-zero, rest all are 0. So this solution whatever you have obtained, that is called a basic feasible solution. And in the basic feasible solution, there has to be exactly m plus n minus 1 number of non-zero. So 4 plus 3, 7 minus 1, 6. So we have also 6 non-zero variables. 6 non-zero variables. Rest all are 0. So this is the method. And now we are checking what is the total shipping cost presently with this solution. The total shipping cost, you can see here, total shipping cost 3 into 3, 9, 7 into 2, 14, 9 plus 14, 9 plus 14, that is 23, 23, 4 into 1, 27, 3 into 1, 30, then you have 8 into 1, then you have 8 into 1, 38, 5 into 2 plus 10, that is 48. The total shipping cost is 48. But we cannot say that this is minimum. So whether this is a optimal solution or not, using the phase 2 solution procedure, we'll check. We got a solution. That is a basic feasible solution. But this basic feasible solution is not saying whether it is minimum or not. Is it clear? Or anything you want to say? Anything you want to ask? Okay. Hello? Anybody? Okay.
Sir,
Yes.
sir, if a row and a column are cancelled simultaneously, means they are satisfied simultaneously.
Yes.
We will get degenerate BFS, right?
Yes. Most likely degenerate. So because you have to mention simultaneously means, let us say we are considering one of them, say other is 0. Okay. 0. So that 0 will create that it is happening something like that. We have a degenerate solution. Okay. Degenerate solution. So in this example, so we are not cancelling any row or column simultaneously. So that is whatever we obtained. So that is not a degenerate solution. If you find instead of 6 non-zero, if you find there are 5 non-zero, so we conclude that the present solution is degenerate. Okay. So same problem. Say we are discussing with the least cost method. See, least cost. So here we have started with the northwest corner cell. Northwest corner cell. Okay. So you see here, this first cell cost is 3 unit. The second cell 7 unit. Then next the 4 unit. Then 3 unit. Then 8 unit. Then 5 units. In this manner we have moved. Okay. So in the least cost method, what is the rule here? So let me discuss first. In this method, we start assigning as much as possible to the cell with the least unit transportation cost. Least unit transportation cost. Then ties are broken arbitrarily. If you find this least, least cost, there are more than one cell, then we can, there is a tie, we can break the tie arbitrarily. And the associate amount of the supply and demand are adjusted by subtracting the allocated amount. Same rule. Cross out the row or column with 0 supply or 0 demand to indicate that no further assignment can be made to that row or column. Okay. If both a row and a columns are simultaneously satisfied, then if exactly one row or column is left uncrossed, make the obvious allocation and stop. Else, cross out one only, either a row or a column, and leaves a 0 supply or demand in the uncrossed row or column. Next, we look for the uncrossed cell with the smallest unit cost and repeat the process until no further allocation are to be made. Okay. See, the same problem we are looking for. You can see, say, what is happening to this? So the cost we are checking. So 3 unit, then 7 unit, 6 unit, 4 unit. Then we have 2 units, 4 unit, 3 unit, 2 units, 4 unit, 3 unit, 8 unit, 5 minutes. Now among all the cost, which one is least? Which one is least? Please tell me. The cost I am talking about, the cost 3, 7, 6, 4, 2, 4, 3, 2, 4, 3, 8, 5. So the least cost equal to 2. There are two different cell. Cell 2-1 as well as cell 2-4. 2-1, the cost is 2 units and 2-4 also equal to 2 units. So with respect to this least cost cell, so there is a tie. We can break. You can take the first one. You can leave the last one, or you can take the last one, leave the first one, whichever you like. Okay. So we are considering cell 2-1. With respect to cell 2-1, what we are doing? So we are allocating as much as possible. So you can see in the same 2-1 means 2-1 correspond to row 2 column 1. So in the row 2, what is the availability? 2 units. And what is the demand? 3 units. So we can allocate only 2 units. So 2 units allocated. Now demand is fulfilled 2 units, 1 unit left. So we have to remove, that is second row is fulfilled. We have to remove the second row. So assuming that nothing is there in the second row, that is fulfilled. Okay. Now what is happening further? So you can see, so the cost we are talking about 3, 7, 6, 4. Second row nothing. 4, 3, 8, 5. And what is the least? Least cost is actually 3. You can talk about this cell 1-1, that is 3 unit. Then cell 3-2, that is also 3 units. Okay. So first come first basis, let us say, if I am allocating to cell 1-1, see how much is there. So in the row there are 5 units, in the column 1 unit. So we can allocate only 1 unit. If you can allocate 1 unit, then we have to cross the first column. We cross the first column. See, second row has gone, first column has gone, and see, once you are allocating 1 unit out of 5, 1 unit has gone. So what is left out? That is 4 unit. Okay. So now see what is happening to this. 7, 6, 4. 7, 6, 4. So second row nothing is there. Then third row 3, 8, 5. 3, 8, 5. So minimum is 3. So we are allocating how much? We are allocating this 3 units. You can see here you are allocating 3 units. So 3 units we have allocated in the row, that is 3. In the column is also 3. So after allocating, we are removing only third row, not the second column. So the 0 unit left out. Okay, 0 unit left out. So the third column is gone. Now third row has gone. Earlier second row has gone. Now first column has also gone. So what is left out? You can see here. See, this is 7, 6, 4. 7, 6, 4. And what else? So 7, 6, 4. So with respect to 7, 6, 4, so you can see here minimum is 2. We are allocating 2. We are allocating 2. So out of 4, the 2 has gone. Only 2 left out. Then what is happening to this? Then next minimum cost is 6. So we are allocating 2. Then how much left? 0 is left. So, and ultimately this last cell you can see here, that is 7, and no allocation to that. So it is 0. So we are allocating in this manner 1. The first row wise I am talking 1, 0, 2, 2. Then we have 2 in second row, there is 2 only. In third row, only 3. So whether it is fulfilled, you add. First row sum is 5, second row sum is 2, third row sum is 3, first column sum is 3, second column sum is 3, and third column sum is 2, and fourth column sum is 2. It is fulfilled. Now, what is happening to this all? Answer. So 3 into 1, that is 3, 7 into 0, 0, 3, 6 into 2, 3 plus 12, 15, 4 into 2, that is 8, 23. Then we have 2 into 2, 27. Then we have, you can see here, 27, 3 into 3, 9, 27 plus 9, 36. Earlier, same problem, minimum cost was 48. Now, using the least cost, the cost is 36. What is the conclusion? Which one is better? Which one is better? Hello?
Second one.
Second one is better. Still, we cannot conclude whether the present solution is optimal or not. Okay. Present solution is optimal or not. Okay. So I would like to mention, so how to check whether the present solution is optimal or not using the duality theory. Okay. Just I am considering this slide again we will discuss. So I am considering a small example. Okay. Small example.
Sir, I have a doubt in the previous step.
Yes, tell me. What is your
Sir,
doubt?
when we remove 3 to 2, like both row and column, the demand and supply becomes 0. So how we decide which to remove, row or column or both?
Which row, which column? So
Sir,
see, we are you are talking about the minimum cost. Yes or no?
Yes, sir.
Minimum cost. So minimum cost, say where, see, we are checking out of, how many cells are there. There are m into n number of cells. Okay. Now you check each of them, which is minimum. Okay. So you'll find at least 1 or 2 or we don't know how many are there, how many cells are having minimum cost. So wherever is minimum, that we should consider. Okay. And there is a tie also. Tie in the sense, so you can say first come first basis or whatever way you can consider, no problem. Okay. You will have a solution. Okay. So in this manner we proceed, but at a times we can only cancel a row, a particular row or a particular column. You cannot cancel 2. And what will happen to that? So if you are cancelling only one, other row or column, the allocation has to be 0. Because at a times 2 means that will create a problem for us because we have to look for a solution. And in the example, if I am coming to this earlier example again, you can see here what is happening. You have asked a right question here. Now see this problem. How many cells we have allocated? 1, 2, 3, 4, 5, 6. How many cells we have allocated? We have allocated exactly 6 cells. Okay. One of the cell, the value equal to 0. So here, if I am mentioning x11 equal to 1, x12 equal to 0, x13 equal to 2, x14 equal to 2, x31 equal to 2, then x21 equal to 2, then x32 equal to 3. One of the variable, that is x12, is 0. What is the conclusion? We have a solution. But the solution has to be exactly, so m plus n minus 1, 3 plus 4 minus 1, that is 6 cell must be non-zero. But we find one of them is further 0. So this is a basic feasible solution, but this basic feasible solution is a degenerate solution. Degenerate because one of them is 0, right? You see, cell number C12. With respect to C12, we have X12 is 0. X12 0 means rest all are non-zero. That is 1, 2, 3, 4, 5, 6. Out of 6 cell, only one cell has a 0 value. So it is a solution, basic feasible solution, but this is a degenerate solution. That's all. Okay. This degenerate solution has some problem. So when you solve problem, we'll discuss what problem we'll face. Okay. So we have to assign that 0 is to epsilon and proceed. Otherwise, there will be a crisis. Okay. Okay. So this is a very elementary transportation problem. How many sources are there in this problem? How many sources are there?
2.
There are 2 sources. How many destinations are there?
2.
There are also 2 destinations. Okay. That is a 2 by 2. Okay. So, and mathematically, if you're writing, the problem is minimize z equal to C11 into X11, C12 into X12, C21 X21, C22 X22, subject to there are 2 source constraints, X11 plus X12 equal to A1, X21 plus X22 equal to A2. Similarly, X11 plus X21 equal to B1, X12 plus X22 equal to B2. Okay, this. So with respect to this problem, say here there is no numerical data. This is a general formulation, and we like to find the dual of this problem. The objective function is minimization type, and the constants are all equally type. And what else? The constants are all equally type, and the decision variables are non-negative. If the objective function is minimization type in the primal, dual will be maximization type. And since the constants are all equally type, in the dual, the variables will be free variables. If it is equally type, then the dual, the variables will be free. So same thing here we are mentioning here. So our dual problem is maximization type. So how to write? So we have dual variables with respect to S1, first row. We are considering a dual variable U1. With respect to second row, we are considering a dual variable called U2. And with respect to first column, we have a dual variable called B1. With respect to second column, we have a dual variable called B2. So there are 4 dual variables we are writing in this manner. Maximize some other objective function, Z prime, A1 U1 plus A2 U2 plus B1 V1 plus B2 V2 subject to, so, and if you can rename these 4 variables, X11, X12, X21, X22, how will rename? Let me name in this manner. X11 equal to, let us say, Y1, X12 equal to Y2, X21 equal to Y3, X22 equal to Y4. And if you rename and proceed, so you can realize we have this type of constants. U1 plus B1 less than equal to C11, U1 plus B2 less than equal to C12, U2 plus B1 less than equal to C21. So U2 plus B2 less than equal to C22. And these variables, how many variables are there? There are 4 variables. These are all free variables. This can be negative, this can be positive, this can be 0 also. They are free variables. Okay. So this will help us. To find the solution. Okay. So now with respect to this problem, so we have already got what? We have got, so in this numerical example using the phase 1 solution, so either by least cost method or by the northwest corner rule, we have got some solution. So that solution you can check whether it is optimal or not. So we have to use the duality theory. So if it is optimal, what will happen? If it is optimal, all these constraints has to be fulfilled. All the constraint has to be fulfilled. Now, there are some problems. There are some problems I have to explain how you can say that these are fulfilled and these are not fulfilled. So you have to realize that. See, we have what? We have allocation. We have exactly m plus n minus 1 number of allocation. Okay, so these many allocations are there. So these many variables are, we assume, let us say positive, let us say allocation. These are the basic variables. Okay, so according to the duality theory, with respect to a particular variables, so as you know, we have to mention something like, say, with respect to this, say, first cell. Okay, this first cell. So with respect to first cell, our constant is dual constant equal to u1 plus b1 less than or equal to c11. So we write in this manner, x11 into u1 plus b1 minus c11, okay, equal to 0. I'm repeating again, with respect to x11, so this is the constant. So with respect to cell 11, so x11 into u1 plus b1 minus c11 equal to 0. Okay, so this has to be 0 always according to the duality theory. So if x11 is 0, it is fulfilled. If x1 is positive, then what will happen to this? If x1 is positive, so if x1 is positive, we will have u1 plus b1 minus c11 equal to 0. If x1 is positive. Similarly, if x12 is positive, then we have u1 plus b2 minus c12 equal to 0. Similarly, if x21 equal to positive, then u2 plus b1 minus c21 equal to 0. If x22 is positive, then u2 plus b2 minus c22 equal to 0. Okay, this condition you have to use. See, we have already taken basic feasible solution. There are how many are positive? We are assuming m plus n minus 1 number of basic variables, they are positive. So these many equality constraints you will have. These many equality constraints. Okay, so these many equality constraints means what is happening to this? Altogether, if you are counting how many u and how many v are there, how many u and how many v are there? There are, with respect to this smaller problem, we have two u1, u2, two variables, and v1, v2, 2 plus 2, 4. So if I'm calculating the number of the basic variable in the basic feasible solution, how many has to be non-zero? How many has to be non-zero? Let me say my solution is non-degenerate, non-degenerate. So there will be 2 plus 2 minus 1. Exactly 3 variables are non-zero. Exactly 3. So which one? For example, one case I'm taking x11, x12, x21. These 3 non-zero, or x11, x12, x22. Out of 4, any 3. Out of 4, any 3 means how many ways? Out of 4, any 3. 4C3. So 4 ways are there. Okay. So we can find these many equations. But how many variables are there? How many variables are there? Our variables x1, x11, x12, x21, x22 already we have got. But how many dual variables are there? There are 4. So we have got how many dual variables? 4 dual variables, but how many equations? How many equations? Because we have got 3 non-zero xij. With respect to 3 non-zero xij, we are getting 3 equations. 3 equations. How many variables? There are 4 variables. 3 equations, 4 variables. It is given that all the dual variables are free. What we should do? We select one of the dual variables 0. One of the 0 or positive, any value you can consider. I'm considering, let us say, u1 equal to 0. Considering one of the variables 0, other variables you can find out. Okay, this is the trick. So here u1, u2, v1, v2 are free variables. So to solve these three equations, we have to find a unique solution. What we should do? Select one of the variables 0, which are, let me say u1 equal to 0. So out of 4 variables, if you are setting one of them 0, we have 3 equations, 3 unknown, we can find the solution. Okay, that's all. Here, the same thing I am discussing here. So let me say out of 4, any 3 are non-zero. So u1 plus v1 minus c11 x11 equal to 0. If x11 is non-zero, then u1 plus v1 minus c11 has to be 0. If x12 is non-zero, then u1 plus v2 minus c12 has to be 0. Similarly, x21 is non-zero, then this has to be 0. And so here we write in this fashion, ui plus bj equal to cij or xij equal to 0. Either this is fulfilled or this is fulfilled. Okay, this. So using this type of equation, 3 such equation, so we'll solve, and one of the variable we set 0 and solve. Okay, that's all. See, this problem, I am giving a hint here. This is a small problem. So if you think about this problem, how many sources are there? How many sources are there?
2.
2 sources. How many destinations are there?
2.
Also 2. So see, it is a very simple problem. So without solving also one can guess, but we are not guessing that manner. We are guessing using the transportation rule. Okay. So with respect to this problem, 200 unit for the first source, 100 unit for the second source, 200 plus 100, 300 units. And you can see here. So destination 150 and destination 150. Okay, this. Okay, right. So if you think about, let us say you are solving the systems. So what is happening to this? We are not applying any method. We are solving the system. So in this manner, minimize z equal to 4 into x11. What is 4? 4 is the cost coefficient. Then 1 into x12, that is x12. 2 into x21. Then 3 into x22. This. Okay. Subject to x11 plus x12 equal to 200. x21 plus x22. This is not 200, it should be 100. Okay, 200, it should be 100 because you know x21 plus x22 it should be 100, not 200. Then x11 plus x21 150, x12 plus x22 150. This fulfilled. Now, if you think about this is there 4 equation for unknown, so immediately you will get solution. Okay, and the second equation, whatever is written there 200, it is not correct. It should be 100. Okay, it should be 100. Okay, there is a phone call. Just 1 minute, please.
Sir, you are muted.
Excuse me, sir. We can't hear you. You are muted, sir.
Sir, you can select that meeting in general and then unmute, sir.
Yes, sir. From here you can unmute.
The right in front you can unmute, sir. Beside leave. Yes, sir.
Now it is okay.
Yes, sir.
Yes, sir.
How this thing happening? Okay, this we are talking. Okay, so if I am considering something like say a new variable, something x11 equal to x1, x12 equal to x2, like this. So this is the problem, and the dual will be like this. Okay, dual will be 200 times u1 plus 100 times u2, 150 times v1 plus 150 times v2. Okay, so subject to the constants are like this. So u1 plus v1 is less than equal to 4, u1 plus v2 less than equal to 1, u2 plus v2 less than equal to 2, u2 plus u2 plus v1, and that is u plus v2 less than equal to this. These are three variables. This is the primal, this is the dual. So with respect to primal dual, and what is the condition we are finding in this manner? u1 plus v1 minus c11 x11 equal to 0. So what I mentioned earlier. Okay, so this will help. See here, I am talking about the northwest kernel rule. Northwest kernel rule. Okay, so with respect to northwest kernel rule, so we are allocating to this cell 150 units. Okay, so once you are allocating, so this first column is gone, that is 0, nothing is left out. And how much we should allocate in the first row, second cell? So only 50 units are left out, so 50. So once you are allocating 50, and how much left out of 150? That is 100 units. So our allocation is like this: 150, 50, 100, 150, 50, 100. Is it all right? So this solution, whatever is presented, this is with respect to northwest corner rule. Okay, solution 150, 50, 100. Okay, this we have got. This is a trial solution, and we like to check whether this solution is optimal or not. Whether this solution is optimal or not. Actually, say what we have obtained. So x11 equal to 150, x12 equal to 50, x21 equal to 0. Nothing is mentioned here. Then x22 equal to 100. These are three allocation. as per the norm, as per the rule, we have 2 sources and 2 destination. That is 4 cells. 4 minus 1, that is 3. 3 are non-zero. What are the values non-zero? X11, X12, X22. Okay. With respect to this, we are checking what is the value. 150 into 4, 600. 50 into 1, 650. Then 100 into 3, that is 300. 650 plus 300, so that is 950. This value we are finding. Now I like to check whether it is optimal or not. Whether it is optimal or not. Now with respect to the first cell, which is non-zero, we have this relationship. U1 plus B1 equal to 4. U1 plus B1 equal to 4. With respect to second cell, U1 plus V2 equal to 1. And with respect to the last cell, you can see here, U2 plus V2 equal to 3. How many equations are there? How many equations are there?
3, sir.
3 equations. But how many variables are there? There are 4 variables. Variables are U1, U2, V1, V2. 4 variables. One of the variables we are setting 0. Which one we should set 0? Let us say U1 equal to 0. If you set U1 equal to 0, what is our V1? Set U1 equal to 0. So V1 equal to 4. So U1 equal to 0, V1 equal to 4. If you are setting U1 equal to 0, V2 equal to 1. Okay. Once you are setting V2 equal to 1, you have got V2 equal to 1, then U2 equal to 2. We have got. Now, after finding this, we'll check whether it is fulfilling or not. Okay. Check for optimality. Check for optimality. See, as per the norm, this has to be fulfilled. What is the fulfilled? U1 plus B1 less than equal to 4. U1 plus V2 less than equal to 1. U2 plus V1 less than equal to 2. Plus U2 plus V2 less than equal to 3. This has to be fulfilled. Okay. So now we are checking. Okay. So we have got U1 equal to 0. V1 equal to 4. U2 equal to 1. And we have V2 equal to 1. Okay. Checked for optimality. Now, so this is cell number 11. Cell number 11 already. These 3, first cell, second cell, and the last cell we have already taken. It is fulfilled. Only we have to check the on with the cell which is not allocated. That is the unmarked cell. Okay. So that is U2 plus B1. U2 plus B1. What is U2? What is U2? So U2 we have got 1. B1 you have got 4. U2 1, B1 4. So U2 plus B1, what is the value? That is 5. U2 plus B1 equal to 5. This 5, but as per the norm, it has to be like this. So U2 plus B1, so it should be less than equal to U2 plus B1. It should be less than equal to 2. But we have got, what is there here? Okay. We have got, it is greater than 3. So this is U2 plus B1, it is 5. That is greater than, okay. So U2 plus B1, it is, okay. So this is less than, so this is greater than 5. So it is violating. So the present solution is not optimal. The present solution is not optimal. Why? Why it is not optimal? So U1 0, V1 4, U2 1, V2 1. So if you substitute the cell which is not allocated, it is not fulfilled. So it is not optimal. Okay, this. Now what is happening here? This is 150, this is 50, this is 100. Okay. Now how to make allocation? How to make allocation? So we have to see this is 150, this is 50, this is 100, and this is nothing is there. So now next work is we like to, this is, according to the simplex rule, this is which is not fulfilled, that is the new entering variable. If this is the new entering variable, one of the variable must be departing variable. This is the new entering variable. One of the variable must be departing variable. So we mark in this manner. Let me say it is plus sign. This is minus sign. We make a loop plus minus plus minus plus minus plus minus. If you increase something, then same amount must be decreased. Okay. So plus minus plus minus. You can see here. So 150, 50, 100. Okay. Now what we should do? So among the negative one, so negative one is 150, another is 100. So you reduce. So after reducing, we have to make it 0. So the 100, if you reduce 100 units, so this will be 0. The 150 will be 50, and same amount must be increased. So this will be the third cell. It will be 100, and which is 50. This is 150. So in this manner. So we have put a mark that is positive plus, and this is 150 is negative. This is positive. This is negative. So make a loop. So after making the loop, so if one of them is reduced, all the negative has to be reduced, and if it is to be increased, all the positive has to be increased, because the loop is like that, alternately positive and negative. So we are reducing out of 150, 100 units. So the 100 unit, this will be 0. 0 means no allocation, and 150, this is 50, and this is, so we have increased. So one will be 50, another will be 150. This is 100. Okay. So the 51, which that is because 150, and which is 0, that was 100. Okay, in this manner. Now this is the present modification. So after doing the present modification, we'll check further. What we'll check? So whether it is fulfilling the primal problem and the dual problem constants. Whether it is fulfilling the dual constants or not. So this is 50, this is 150, this is 100. This third one, the fourth cell is empty. So we have to calculate in this manner. U1 plus V1 equal to 4. You can see here. U1 plus V1 equal to 4 with respect to the first cell. Then U1 plus V2 equal to 1, second cell. Then the third, U2 plus V1 equal to 3, the third cell. And there are 4 variables, 3 equation, one of them 0. So U1 0, V1 4. Then U2 minus 1, V2 1. So we like to check what? We check this fourth cell, that is U2 plus V2 has to be less than or equal to how much? 2. So U2 plus V2 has to be less than or equal to, but we find here U2 plus V2 equal to 0. 0 is less than or equal to 2. So that is fulfilled. So that is optimal. Okay. So with respect to this optimal solution, you can see here x1 50, x1 150, x2 100. With respect to this solution, our z value, the minimum value of z equal to 650. Earlier it was 950. And if you talk about the dual solution, that is also becoming 650. So that is the optimal solution. Okay. I am repeating again. So,
Sir.
Yes.
Sir, after getting, like, how are we deciding that U1 will be 0?
No. Here, this is a very good question here for you. So what I'm saying here. So in this case, in this problem, there are altogether 4 cells, right? Out of 4 cells, so if we are talking about the basic feasible solution, 3 cells, the variable has to be non-zero. Okay. Variables are x11, x12, x21, x22. Okay. This 4 out of 4, 3 are non-zero. So any 3 may contribute. Any 3. Okay. So with respect to this, If I'm saying x11, if I'm saying x11 is non-zero, then what is the condition? u1 plus b1 minus c11 equal to 0. x12 is non-zero, then u1 plus b2 equal to c12. x21 equal to non-zero, then u2 plus b1 minus c21 equal to 0. Now, I have mentioned there are 4 variables, 3 equations. But in the dual program itself, I have mentioned here also, all the variables are free. Free variable says they can be positive, they can be negative, they can be 0. Free variables. Okay. So any variables you can make 0. Any variables you can make 0 and proceed. Okay. Which one you can make 0? You can make u1 0, u2 0, or v1 0, or v2 0, whatever. Generally, according to our procedure, we are setting u1 equal to 0. You can, instead of 0, you can take 1 also, a constant, no problem. Okay. They are free variables. So we are setting u1 equal to 0 and finding the value. Okay. So after finding the value, we check the dual constraint with respect to which cell? With respect to, see, all of them, all are contributing, and which is not contributing, that we check whether it is fulfilled or not. If it is fulfilled, the solution is optimal. If it is not fulfilled, solution is not optimal. We have to reallocate. That's all. Okay. Any other? Though it is a very elementary problem, the trick is here. What is the trick? The trick is, so first, with respect to the primal problem, we are formulating a dual program. Okay. So with respect to the non-zero variables, allocated variables, we are using this type of conditions, and we are writing u1 plus b1 equal to c11 because x11 is non-zero. Similarly, u1 plus b2 equal to c12 if x12 is non-zero. So we have 3 such equations. And how many variables? There are 4 variables. But in our general problem, we will have m plus n minus 1 such equation. But how many variables? There are m plus n number of dual variables. The dual variables are namely u1, u2 up to um, v1, v2 up to vm. So altogether m plus n number of dual variables. So if one of them 0, so we can find the unique solution for this system. And after finding the system solution, you check all these constraints has to be fulfilled. Already few of them we have taken. Only which is not taken, that you check. Out of 4, 3 already you have taken. So which you have not taken, that you must check. If it is fulfilling, then it is the optimal solution. If it is not fulfilling, we have to reallocate. That's all. Okay. Anything else? Okay. So I am coming to, this is the example which I have taken to explain you. So I am coming to the general problem. Okay. See here. Transportation problem, phase 2 solution known as Modi's method. Modi stands for here modified distribution. Okay, modified distribution method. Iterative computation of transportation algorithms. After determining the starting basic feasible solution by any of these method, maybe northwest corner rule or least cost method or any other method. So we find the basic feasible solution, which has exactly m plus n minus 1 number of non-zero solution. Okay. So use the simplex optimality condition to determine the entering variables and the current non-basic variable that can improve the solution. If the optimality condition is satisfied by all the non-basic variables, the current solution is optimal and we stop. What I explained in this small example. Okay. Otherwise, go to step 2. Step 2, determine the leading variable using the simplex basic feasible condition. Change the basis and go to step 1. The determination of the entering variable among the current non-basic variable is done by method of multipliers. Okay, what I have mentioned here. In this method of multiplier, we associate with each row a dual variables, namely u1, u2 up to um, and similarly for the column we associate dual variables like v1, v2, vm. So note that each row corresponds to a constraint and each column corresponds to a constraint. We recall from the duality theory that, okay, something like here we are mentioning zij minus cij. Okay, this actually ui plus bj minus cij. Zij, okay, we are naming this minus cij. This is equal to say ui plus bj minus cij. This actually has to be 0. So if this is 0, if zij minus cij equal to 0, then we write here ui plus bj equal to cij. Cij is given, uia and baj are non-known, and we have altogether m plus n number of variables. Set one of the variables 0 and proceed. Okay, this. So we determine m plus n dual variables. We arbitrarily choose one of them equal to 0 and determine the remaining m plus n minus dual variables. Okay, so that I have mentioned. If you consider a maximization type transportation problem, instead of most positive element, we take, so this I am not talking, we are taking only minimization type problem. Okay, so this is a problem you can see here. Another problem. So this problem, we have got solution, let us say using northwest corner rule. Northwest corner rule, we have got solution, and this solution we have to check whether it is fulfilling or not. It is fulfilling. Okay, how it is fulfilling? 3 plus 2 equal to 5, 1 plus 1 equal to 2, 1 plus 2 equal to 3, row wise, and column wise 3, then 2 plus 1 3, then 1 plus 1 2, then 2 it is 2. So total supply is 10 units, 5 plus 2 plus 3, total demand equal to also 10 units. Now in this problem, what we should do? So we are calculating the value of what? Value of the dual variables. See, u1 plus b1 equal to 3. See here, u1 plus b1 equal to 3. If u1 equal to 0, b1 equal to 3. Clearly mentioned. Now similarly, move to the second cell. u1 plus b2 equal to 7. Since u1 equal to 0, b2 equal to 7. Okay, b2 equal to 7. So now what we are doing, we are checking the other one also. So this cell, that is the cell number C22, that is u2 plus b2 equal to 4. b2 equal to 7. Since b2 equal to 7, we have got u2 equal to minus 3. Okay, so b2 equal to, just now we have got 7, so we find u2 equal to minus 3. Now next cell, that is cell number C23, that is u2 plus b3 equal to 3. So u2 plus b3 equal to 3. Since u2 equal to minus 3, we find b3 equal to 6. Okay, because u2 plus b3 equal to u2 plus b3 equal to 3. So since u2 equal to minus 3, we find b3 equal to 6. So this is done. Now similarly, we have here cell number C33. u3 plus b3 equal to 8. Since b3 equal to 6, so we find u3 equal to 2. And finally, we have last cell u3 plus B4 equal to 5. Since U3 equal to 2, we find B4 equal to 3. So we have got here what? So 3, value of U1 0, U2 minus 3, U3 2, B1 3, B2 7, B3 6, B4 3. Now, out of these 12 cells, 4 into 3, 12 cells. So 6 are allocated. 3, 2, 1, 1, 3, 2, 1, 1, 1, 2. The rest, all the cells are not allocated. We have to check. We have to check. How do we check? So we have to check which one is fulfilled and which one is not fulfilled. So among that, so it is mentioned here, X32 enter the basis. See what we are doing. So most negative. So in the simplex there is a term called most negative and most positive. So we have our fulfillment. Our fulfillment, as you know, UI plus Bj is less than equal to Cij. Ui plus Bj less than equal to Cij. So the left hand side must be fulfilled with the right hand side. If you find, so the left hand side, so it is more, right hand side is less, there is negative. Okay, so whichever is giving the most negative, that should be considered. You can see here. Now I'm talking about, see, X32. X32, that is the third row and second column. Third row, second column. So third row, second column. So what is U2 equal to 3 and B2 equal to 7, U2 plus U3 plus B2, that is 2 plus 7, 9. So, and what is that? 9 cannot be less than equal to 3. 9 cannot be less than equal to 3. So 9 minus 3 is coming as 6 unit. So negative, that is 6 unit negative, this. And now 6, that minus 6 we are finding. Now if you are coming to this first cell, that is first row and third column, you can see here, first row, third column. So first row, third column says U1 plus B3. Okay, U1 plus B3. So U1 plus B3. U1 equal to 0, B3 equal to, B3 equal to 6. So that is fulfilled. So we will not consider which is fulfilled, which is not fulfilled. So this is not fulfilled, that is the reason you consider. Okay, this. So X32 enter the basis. Now with respect to this, we are making some cell like this. So with respect to, we are making some cell. Okay, this theta is unknown. This is so a entering variable, and a cell means forming a closed loop. So this is, let us say, positive, then it is negative, then positive, negative, positive, positive, negative, positive, negative. Okay, all the positive must increase, all the negative must reduce. So you can see here, this 1 1, this 1 1, this 1 1, we can reduce to 0. One of them you can make 0, and this theta, which is 0, we make positive. Okay, so the theta with 0 we make positive. As a result, we have like this. You can see here. So 0, one of them 0, this is 1, and further there is some allocation. Okay, so once you have reduced, so we'll check whether the given solution is optimal or not. If it is optimal, we stop. If it is not optimal, so presently the cost was 48. Now you can see here what is happened. This present, next time the cost is becoming 42. Okay, this is the loop, and further we have, so there is no changes. So here we find the cost is 32. And what is the conclusion here? This is the optimal table. So we are mentioning here, this is the optimal solution. So why optimal solution? Now I want to just check here. Okay, check. See, what are the allocated cell? 1, 2, 3, 4, 5, 6. There are 2 0. The 0 can be also our basic variables, but we have made it 0 because if it is becoming, if you are not considering their value, then we will not be able to find all the multipliers like V1, V2, V3, V4. We cannot. So 0 technically we are naming as epsilon, a small positive number. Later on you can make them 0. So with respect to C, so U1, if you set 0, our V1 equal to 3. So once you are saying U1 equal to 0, V2 equal to 7, and V3 equal to 6, and V4 equal to 4. Okay. So and now we want to check whether, and similarly, so U2 equal to -3, so U3 equal to -4. Any cell you can check. For example, I am checking this cell. So U2 plus V1. U2 equal to -3, V1 equal to 3, 0, 0, okay, 0 less than 2, fulfilled. Similarly, U2 plus V2, -3 plus 7, that is 4, 4 is less than or equal to 4, this is also fulfilled. Now, in the second row, the last one, that is U2 plus V4, -3 plus 4, that is 1, 1 is less than 2, that is also fulfilled. Okay. Now last row, that is U3 plus V1, -4 plus 3, that is -1, -1 less than 4, that is also fulfilled. And similarly, we have here next cell, that is U3 plus B3. So -4 plus 6, that is 2. 2 is less than 8, that is also fulfilled. And U3 plus B4, that is 0, 0 is less than 5, this is fulfilled. So the present solution is optimal because it is fulfilled. Same thing we have written here, you can see. Okay, so U1 plus B1, 3. Okay, the 0, 0 minus 3, 2, 3, 7, 6, 3, 0 minus 3, 0 minus 3, 4. Okay. Okay, so you can also, okay, so this is the first one. In the first time we got 48, then second time it is 42, third time it is 42, and finally we have got 32. So this manner we have to check, and we have got the optimal solution. So all the steps are here. Okay. Anything you want to ask here? Hello?
Sir,
Please.
sir, after we get to know what is the leaving variable, how do we modify the table?
You see, I will tell you like this. Okay. So this is a allocation. Okay. This is allocation. So the allocation is like this. So after getting the allocation, okay, wait. Once you got the allocation, so now your question is how to modify the table. Okay. So what is a dual constraint? Dual constraint say ui plus bj less than or equal to cij. Okay, ui plus bj less than or equal to cij. Now what is the difference? So the difference has to be what? The difference has to be this minus this. This is less, no negative. Okay, so if it is negative, so it is fulfilled. If it is negative, okay, but in case you find this is becoming positive, this is positive. Okay, so we are solving minimization type problem. Maximization type problem. So select the most negative element in the indicator row. Most negative element. This is a minimization type problem. So we will select most positive element. Okay, ui plus bj minus cij. You calculate for all other than the allocated cell. 1, 2, 3, 4, 5, 6. Out of 12, this 6 you leave. How many are left? How many are left out? Out of 12, 6 already have left. Then another 6 are left. Okay. So for all the 6, you calculate ui plus bj minus cij. Which is most positive? The difference is most positive. That is the entering variable. If there is a tie, you can break. Okay. Entering variable we have got. Now what is the departing variables? We make a closed loop. How closed loop? We'll select the closed loop means this is the theta, wherever I mentioned theta, that is the entering variable. Now see in the table how many are allocated variables. Okay, so we have to form a closed loop by drawing horizontal and vertical lines. One of them is not allocated, that is theta is not allocated, rest 3 are allocated. Okay, here for the closed loop, this is the ideal condition, but there may be other type of closed loop. Okay, so you have to make horizontal and vertical so that number of vertices with positive mark and number of vertices with negative marks are same. Whatever we increase, same thing is decreased. Okay, so here this is also, you can see here. So this we have not taken. If this is theta, we can have like this. Okay. Okay. So there may be other position also, you can see, but here this is theta and this is all allocations. So one of them not allocated, rest are all allocated, and this 0 and these 2 we have not considered. Not necessarily any 3 you have to select. So that you can visualize from the problem. Okay, manual we are doing, you can visualize from the problem. Okay, so how you can visualize? Because you see, you have to draw horizontal and vertical lines so that you make a closed loop. Okay, closed loop. And please remember, which is the entering variable? Where you find ui plus bj minus cij is most positive. Okay, if it is 0, it is ideal. If it is equal to, if it is negative, it is ideal. If it is positive, it is not fulfilled. So this, if you see here itself, so ui plus u1 plus b1 equal to 13. So using all these 6 condition, we are finding all the dual variables. One of them 0. Okay. So, but how we are checking? We are checking in this manner. So this 6 you have got u1 plus b3, u1 plus b3. So what is u1? u1 equal to 0 and b3 equal to 12. 0 plus 12 equal to 12. Now this 12 u1 b3 with respect to this position u1 b3. So and we find that is greater than 6. The cost coefficient is 6. So it is greater than. So if it is less than or equal to 6, it is fulfilled. It is greater than. Okay. So greater than 12. Then we find this is 12. This is 9 minus 6 minus 6. Among this, which is maximum? Maximum is 12. So due to that, so this is our entering variable because it is plus 12. Plus 12 plus 9 minus 6 minus 2. So this 0. Okay. So once you are saying negative or 0, it is fulfilled. When you find positive, that is not fulfilled. Among all the positive, which is the most positive, that should be our entering variable. That's all. Anything else? This only two cells are not fulfilled. Rest all are fulfilled. So due to this, so you can select this one, the theta. That is the theta is the entering variable. Okay. So that is the new x, and make a closed loop and proceed. I will solve more problems. Okay. Anything else? I'll stop here.
Can you share these notes?
Okay. Thank you.